In the previous two videos, I looked at arithmetic progressions and finding the nth term for specific sequences. I want to take one final look at this work to find the general rule for the nth term of arithmetic progressions. I'm then going to use this approach to look at finding the nth term for another type of sequence. I have put a link in the description below to the previous videos on arithmetic progressions. Here are two arithmetic progressions, and here are the general rules for those arithmetic progressions. To understand how I found the nth term for those two progressions, you need to look at the previous videos. But we're now going to look at these two progressions slightly differently to find the nth term. I'm going to set it out like this. So the first term is 3. The second term is 3 add 2. The third term is 3 add 2 add 2. The fourth term is 3 add 2 add 2 add 2. The fifth term is 3 add 2 add 2 add 2 add 2. And we'll write down the sixth term, which is 3 add 2 add 2 add 2 add 2 add 2. Let's look at the sixth term. Look at how many 2's have been added to our original term of 3. For the sixth term, 5 2's have been added. Let's rewrite this as 3 add 5 multiplied by 2. Looking at the fifth term in our sequence, we have the first term of 3, and then we've added 4 lots of 2. So let's write this as 3 add 4 multiplied by 2. With the fourth term, we have 3 add 3 lots of 2. And we can do the same for the third term, so that's 3 add 2 lots of 2. And for the second term, that's 3 add 1 lot of 2. And then of course for the first term it's just 3. Do you spot a pattern? For the second term, we added 1 lot of 2. For the third term, we added 2 lots of 2. For the fourth term, we added 3 lots of 2. For the fifth term, we added 4 lots of 2. For the sixth term, we added 5 lots of 2. So if we were writing down the nth term, this will be 3 add n minus 1 lot of 2. And look what happens if I simplify this nth term. Well, we'll multiply the brackets out. So that's 3 add 2n subtract 2. And then that simplifies to 2n add 1, which is what we've got up here. I'm now going to repeat this process for this arithmetic progression and see if we get the same nth term of 3n subtract 2. So for this progression we're adding 3 each time. If you want to have a go at this yourself, then pause the video and when you're ready, press play. So our first term is 1. Our second term is 1 add 3. Our third term is 1 add 3 add 3. Our fourth term is 1 add 3 add 3 add 3. Our fifth term is 1 add 3 add 3 add 3 add 3. And our sixth term is 1 add 3 add 3 add 3 add 3 add 3. And we can see that for the second term of our sequence, we added 1 3. For the third term of our sequence, we added 2 lots of 3. For our fourth term, we added 3 lots of 3. For our fifth term, we added 4 lots of 3. And for our sixth term, we added 5 lots of 3. So for our nth term, this is going to be 1 add n minus 1 lot of 3. And if we simplify this nth term, well, we multiply out the brackets, so we have 1 add 3n subtract 3, and then that simplifies to 3n subtract 2, which is what we've got up here. From these two examples, I'm going to create a more general rule for finding the nth term for arithmetic progressions. We're going to allocate a letter for the first term, and we're going to use the letter A. And for the difference between each term, we're going to use the letter D. And so for the nth term, we can write a general rule for arithmetic progressions of A add n subtract 1 all multiplied by D. So if I wanted to find the nth term of this sequence here, well, the first term is 2, and the difference between each term is 5. So the nth term is 2 add n subtract 1 all multiplied by 5. And this simplifies to 2 add 5n subtract 5 if we multiply out the brackets. And this is equal to 5n subtract 3. I want to take this idea forward to look at another type of sequence. Have a look at this one. In this example, we can see that the difference between the terms is different. But can you see another relationship that gets us from one term to the next? You can probably see that the next term is 2 times the previous term. 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, and so on. Where the terms are created by the use of a constant multiplier, which in this case is multiplied by 2, this is called a geometric progression. Let's find a rule for the nth term for this geometric progression, using what we'd done previously for the arithmetic progression. So our first term is 3. Our second term is 3 multiplied by 2. Our third term is 3 multiplied by 2 multiplied by 2. The fourth term is 3 multiplied by 2 multiplied by 2 multiplied by 2. The fifth term is 3 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 2. And the sixth term is 3 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 2. Now, using what we know about powers, we can simplify these terms. Well, the first term is still 3. The second term is 3 multiplied by 2, which can also be written as 2 to the power of 1. The third term can be written as 3 multiplied by 2 squared. The fourth can be written as 3 multiplied by 2 to the power of 3. The fifth can be written as 3 multiplied by 2 to the power of 4. And the sixth term can be written as 3 multiplied by 2 to the power of 5. And again, we can see a relationship, this time between the pattern number and the power. So for the second term, we have 2 to the power of 1. For the third term, we had 2 to the power of 2. For the fourth term, we have 2 to the power of 3. For the fifth term, we have 2 to the power of 4. And for the sixth term, we have 2 to the power of 5. So for the nth term, this is going to be 2 to the power of n minus 1. That is 1 less than the pattern number. So the nth term is going to be 3 multiplied by 2 to the power of n minus 1. Here's another geometric sequence. I'm going to find the nth term for this sequence. But if you want to have a go at this yourself, then pause the video and when you're ready, press play. First of all, we can see that this is a geometric sequence because to get from one term to the next, we are multiplying by 3. The first term we can write down as 2. The second term we can write down as 2 multiplied by 3. The third term we can write down as 2 multiplied by 3 multiplied by 3. The fourth term we can write down as 2 multiplied by 3 multiplied by 3 multiplied by 3. And we can repeat this for the fifth and the sixth term. So simplifying these terms, we have 2. We have 2 multiplied by 3 to the power of 1, or 2 multiplied by 3. For the third term, we have 2 multiplied by 3 squared. For the fourth term, we have 2 multiplied by 3 to the power of 3. For the fifth term, we have 2 multiplied by 3 to the power of 4. And for the sixth term, we have 2 multiplied by 3 to the power of 5. Again, as with the previous example, there is a relationship. For the second term of this sequence, we had 3 to the power of 1. For the third term, we had 3 to the power of 2. For the fourth term, we had 3 to the power of 3. For the fifth term, we had 3 to the power of 4. For the sixth term, we had 3 to the power of 5. And so for the nth term, we're going to have 3 to the power of n minus 1. So our nth term for this sequence is 2 multiplied by 3 all to the power of n minus 1. And if we compare the nth term of both of these sequences, we can actually generate a general rule for geometric progressions. Again, the first term will be the letter A, but this time we have a multiplier. That is the number that we are multiplying each term by to generate the next term. And for this we're going to use the letter R. So the nth term is equal to A multiplied by R all to the power of n subtract 1. So looking at this example here, 1, 5, 25, 125, 625, if we had to find the nth term for this geometric sequence, we can see that we are multiplying by 5 each time to generate the next term in the sequence. 1 multiplied by 5 is 5, 5 multiplied by 5 is equal to 25, and so on. So our first term is 1, and our multiplier is 5. So plugging this into our general rule, the nth term is going to be 1 multiplied by 5 to the power of n subtract 1. So if you were asked what is the 30th term of this sequence, well, this would be 1 multiplied by 5 to the power of 30 subtract 1, which is equal to 1 multiplied by 5 to the power of 29. Of course, this would generate a very large number, so it would be okay to leave it in this form. Have a look at this sequence here. We have 40,000, 4,000, 400, 40, and 4. What do you notice about this sequence? Well, we can see to get from one term to the next term, we are dividing by 10 each time. So the first term is 40,000. The second term is 40,000 divided by 10. The third term is 40,000 divided by 10 divided by 10. And the fourth term is 40,000 divided by 10 divided by 10 divided by 10. And again, we have a relationship. For the second term, we have 40,000 divided by 10 to the power of 1. For the third term, we've got 40,000 divided by 10 divided by 10, which is the same as 40,000 divided by 10 to the power of 2. And for the fourth term, we've got 40,000 divided by 10 divided by 10 divided by 10. Well, divided by 10 divided by 10 divided by 10 is the same as divided by 10 to the power of 3. And we can see that for our nth term of this pattern, it's going to be 40,000 divided by 10 to the power of n subtract 1, where 40,000 is our first term and 10 is our multiplier. And we can write this in a more general way of the nth term is equal to a divided by r to the power of n subtract 1, which we can write as a over r to the power of n subtract 1. So that's the nth term for geometric progressions where we are dividing by a constant multiplier. So anyway, there's a brief look into geometric sequences and finding a general rule for both geometric and arithmetic progressions. I hope you found this video helpful. If you did, don't forget to like and subscribe, and thank you for watching.